All right, hello everybody. Today we are finally doing a gradient divergence in curl video. And I should be very good at this video by now because this is the third time I am making this video because the other one didn't record any audio and the other got corrupted. But let's just get into it. You're all excited for gradients, divergence, and curl. So first, we got to define what this is. You see it next to all those things. This is the del operator, or the grad operator, whatever. You can call it anything you want. And it's most helpful to think about it as a vector of partial derivatives. And I know this isn't a vector. A vector kind of needs like actual values, but if you imagine it is one, it makes everything here on out easier. So that's what this is. And all three of these operations we're going to do can be expressed in terms of this del operator. And first up is the gradient. And the gradient, what it does is it takes a scalar function, take the gradient of a scalar function f of x, y, z, and you get a vector field output. And it's super easy to calculate, really. All you do to calculate the gradient is just take the partial derivative of x in the I direction plus the partial derivative of y in the j direction plus the partial derivative of z in the k direction. And that is your gradient. And this is very helpful being able to flip-flop stuff like this, but we know how to compute gradient. That's easy. You're looking at it right now. It's really easy. It's important to understand what the gradient really is. So let's look at this function. F is equal to x squared plus y squared. It's this big paraboloid. We'll solve it easily. I just showed you how to do that. You probably do it in your head. We'll get this vector field 2x and 2y. And if we plot this, we can see how the vectors are moving further and further away, as this vector field would suggest. And that correlates to the steepness of this paraboloid. So really, what we're doing is just representing the steepness almost of a function as a bunch of vectors. So these vectors increase, they get steeper and steeper, just like this big paraboloid. That's the gradient. That's the best way I could put it. All right, what the divergence is it tells you how vectors are moving away from a certain point. So you look at this vector field here, and all these vectors are being pushed away from this center. Imagine there's like a fluid here, and these vectors represent the flow of that fluid. It could be anything, water, probably water, but there's a million different things. So this would have a positive divergence because everything's being pushed away from that center. It's diverging away. They're really intuitive names. And this vector field would have a negative divergence because rather than being pushed away, everything's being sucked in to that point at the center. It's like a sink, all the fluids flowing in. And this vector field here would have no divergence, a divergence of 0, because nothing's being pushed in or pulled away, it's just spinning around, it's rotating. And divergence is also really easy to calculate. It's just, you think of this, our gradient vector from before, partial, partial x, extend this in the bottom because I write big. partial y, partial z. And just like you would with any other vector, you take the dot product. You know how to take the dot product. It's easy. Of f1, f2, f3. And you take the dot product of this, and turns out the divergence is just partial f1 partial x plus partial f2 plus partial over partial f2 partial y plus partial f3 partial z. That's it. Very easy to compute. It's important to remember that just like how gradient, for that we get a scalar function, we put that in, and out we get a vector function or vector field. This we put in a vector field, and we just get a scalar function for divergence. So kind of opposite thing. And for our last operation, whatever, curl, this one will give us, we put a vector field in and we get a vector field out. And what curl is rotation around a certain point in the vector field. So think back to this kind of vector field we had from before. This would have a curl. It would have to. It's rotating. Well, this vector field, also from before, the divergence, nothing here is rotating. There's no curl. So curl is like a measure of rotation in a vector field. Once more, you can imagine the fluids again. These fluids are spinning around as a curl. Ones that are just getting pushed away and not spinning at all, no curl. And curl, just like the divergence, is calculated by taking the cross product of the gradient vector and whatever you're working with. So we'll draw our big, ugly 3x3 matrix here. And to find the curl of any given vector field, you just take the determinant of this matrix, which was very long, and I will write it now. And boom, there you have it. Determinant of a 3x3 matrix. Kind of long, but whatever. It's still easy to compute. Just more writing. All right, thank you all for watching the gradient divergence curl video. It's finally out. I'd like to do more videos of this stuff. Vectors are cool. Each individual one of these operations could get their own video, and the secret fourth operation that I didn't talk about because no one cares. I'm sorry I'm posting this so late. I know you probably have like a day off work, school tomorrow. If I posted it earlier, everybody would just be watching this. But is what it is. At least you have it. Hope you enjoyed. I know you enjoyed it because it's really good. Um, I'll see you next time. See you for the rest of the operations. Goodbye.